Okay.
Alright, now we would now like to examine another measurement instrument which is called Wheastone bridge. Now a Wheastone bridge consists of 4 resistors which we call them R1, R2, RS and RX. Okay? Now the working principle of a Wheastone bridge is that RX is actually an unknown resistor. That means it's a resistor that you want to determine what it is. And we know the resistor value R1, R2, okay, we know the value. And this is a variable resistor, so we can adjust the value. And the working principle is that we adjust this value until there's no current. That means your galvanometers is actually a moving coil meters, right? So you adjust until the pointer says that there's no current. That's the point that you stop. And when you stop, of course, you know the value of RS already, right? So Wheastone bridge circuit is that you know the value of 3 resistors, you have 1 unknown resistor to be measured. And by voltage divider or by Ohm's law, it can be proven that R1 multiply Rx is equal to R2 multiply Rs. Okay? So in other words, the 2 resistors diagonally across the product. So R1 multiply Rx is equal to R2 multiply Rs. Right? So if I know the value of R1, I know the value of R2, I know the value of Rs, Rx can be found. So therefore Rx can be found. So that is called the Wheastone bridge when it is at a balanced condition. Balanced condition means no current flow. No current flow. Right? So that is called the Wheastone bridge in the balanced situation. Now the second situation that if you want to talk about Wheastone bridge is that it's not balanced, okay? Imbalance. When the circuit is not balanced. Now when it's not balanced, that's called unbalanced condition. Then the methods to go through it is no longer the same, right? So in other words, this previous condition that we talked about no longer hold. Okay, again you have the Wheastone bridge circuit here, and this is unbalanced. Unbalanced means there is a potential difference between these 2 points. So there is a current passing through it. Right? And this current that passes through it, we need to find out. So in other words, to find out how much the current passes through this circuit, you need to go through a series of mathematics to do. Okay, let me just go through one example of a Wheastone bridge circuit, right? So balanced condition. So now we are talking about the unbalanced condition. Now when it's unbalanced condition, we need to find out what is this current Ig here, and this is the internal resistance here. We have the Rg, internal resistance. So when the circuit is not balanced, there is a current passing through it. So we need to change this circuit into a Thevenin equivalent circuit. And the Thevenin equivalent circuit is an ETH and RTH, alright? And then connect to your Rg, alright? So this is your Rg, the internal resistance of the galvanometers. Okay, now if I know this value, and I know this value, do you think I'm able to find out this current Ig? Of course. Ig therefore is equal to ETH divided by the total resistance, and I can get the answer out. Correct? And if I were to say that the galvanometers sensitivity, right? Say for example, if I say that these galvanometers, these moving coil meters and the galvanometers has a sensitivity of 5 millimeters per microampere, right? And let's say that the answer that I calculated Ig is equal to 3 microampere. Then do you know that the meter would have moved how many millimeters? Therefore, the meters would move 1 microampere, 5 millimeters. 3 microampere, 15 millimeters, right? So 3 times 5 millimeters. So they will move 15 millimeters. Okay? Understand? Before I explain to you how to calculate ETH and RTH, let's get the concept correctly first. that I have a Wheastone bridge circuit, now it's unbalanced. Unbalanced, there is a current. Just now balanced, there's no current. No current, the condition to find unknown resistance was pretty easy, right? R1 multiply Rx equal to R2 multiply Rs. But now it's unbalanced, there is a current flow. Okay, we need to know how much current flow through it, right? To do that, we say that we have to transform the circuit into a Thevenin equivalent circuit with a Thevenin voltage, Thevenin resistance, assuming that we have found the values. And I know the internal resistance of the galvanometers. I'm therefore able to find this current. This is a simple series circuit. Total current is the total voltage divided by total resistance. Example, I got 3 microampere. And the galvanometer has a sensitivity of 5 millimeter per microampere. In other words, if there's a 1 milliampere flowing through, the meter will move by 5 millimeters. If it's 3 microampere, it therefore move 15 millimeters. Okay? So now our job now is to how to find ETH and RTH. Now to find RTH, I take it as you take it as a method can be actually be derived and to be proven how to find RTH. Now RTH actually can be found. The method is actually using these two adjacent resistors. Okay, it is R1 parallel with RS plus R2 parallel with RX. Okay, so take it that is a method that you must remember. So it's these two that's parallel to each other. In this circuit, you cannot see that it's parallel. You must bring to Thevenin equivalent circuit, then you can see, right? And R1 is parallel to this, R2 is parallel to this. Okay, so say for example, you know the value resistance. This is 1000 ohm, 500 ohm. Let's say 1000 parallel with 500 ohm. Alright, and then these two resistors parallel with each other. Okay, now to find parallel resistance, I'm sure you already know the method. The shortcut will be R1 times Rs over R1 plus Rs. This is a shortcut method. Okay, R2 times Rx over R2 plus Rx. Of course, you have the traditional method, which is 1 over R1 plus 1 over Rs inverse. Yeah, the traditional method will be like this. Inverse. Yeah, they will be the same answer. So that is RTH. Alright, so we therefore know how to calculate RTH. Okay, how about ETH? To calculate ETH, let me erase this. It also can be proven mathematically how to find ETH. Right? ETH is using voltage dividers formula. So it's actually the voltage across here. So it's Rs over Rs plus R1, right? Times the 5 volt. Okay, times 5 volt minus Rx over Rx plus R2 times 5 volt. It's actually a voltage dividers formula. Yeah. So to simplify it, it actually is Rs over Rs plus R1 minus Rx over Rx plus R2, and then multiply my supply voltage, the supply voltage here, which is 5 volt. Okay. So once I know ETH, I know RTH, I know the internal resistance of the galvanometers, I can find IG. Got it? Okay, so let us revise with the example with numerical answer, numerical values. Right? Let me go through the example in your notes. Yeah, given this is 1000 ohm, 1000 ohm, and this one is 100 ohms. Okay, and you are told that this galvanometer has a sensitivity of 5 millimeter per microampere, and the internal resistance is equal to 100 ohms, right? And the battery voltage is 5 volts, so this is 5 volts, right? Right. Part A, you are asked to find what should be the RSB when Rx is equal to 200 ohm. Okay, you are told that this is equal to 200 ohms. So what should be RSB? right? When the circuit is balanced. Okay, so when in balance condition. Okay, balance condition, what was the formula? This multiply this equal to this multiply that, right? So we say that 1000 multiply 200 equal to 100 multiply RS. This multiply this equal to this multiply this, right? So therefore, RS can be found, right? So I found out my RS, and the answer is equal to 2000 ohm. Okay, 2000 ohm. Right. Part B say, alright, the circuit is going to be having a bit of unbalance with a 5 ohm. In other words, you are going to adjust this to have a little bit more. That means 2005. Okay? When RS is equal to 2005 ohm. Okay? You are asked to find what is IG. And what's the current now? Because just now when it was RS is equal to the value given to 2000 ohm, it was balanced, no current. Now if I adjust a little bit, become 2005, the meter is going to move. And the question asks you how much the movement is going to be. So we need to calculate IG, right? So to calculate IG, what do we need to do? We need ETH, we need RTH, right? So we go back and say find RTH. How do we get RTH? If you recall, these two parallel plus these two parallel, right? So RTH is equal to 1000 parallel with 2005 plus 100 parallel with 200. Okay, so that is the method to calculate the RTH. Okay, and with that you get 733.9 ohm. Alright, of course I'm referring to the notes. To find ETH, again is the method. Remember, it's a voltage divider formula. So it's this divided by this. So ETH is equal to 2005 divided by 2005 plus 1000 minus 200 divided by 200 plus 100 multiply the 5 ohm. So I get an ETH which is equal to 2.77 millivolt. So in here, I already know the value. I know this. And RG is given. Alright, RG is given. Can I find IG? Of course I can. Alright, so therefore, IG is equal to ETH divided by RTH plus RG. Right? So that gives you 2.77 millivolt divided by my RTH 733.9 plus RG 100, and that gives me IG is equal to 3.32 microampere. Right? And we are told that the movement is 5 millimeter per microampere. So how many millimeter does it move? Right? So the meter moves, the pointer moves 3.22 times 5 millimeters. Okay, and that is equal to 16.6 millimeters. Okay, so that is this examples in your notes. So do you think you understand Wheastone bridge? Let's come back. A Wheastone bridge consists of 4 arms. When it is balanced, no current flow. There is no current flow, what is the method? This multiplied by this equal to this multiplied by that. Right, for you to find any unknown. When it is not balanced means there is a current flow. And in order to solve the problem, you have to come up with your Thevenin equivalent circuit. ETH, RTH, right? And then from there you can find the IG, the current through the galvanometers. How to find ETH and RTH? This is the method. Remember it and then work on it to try a few questions, and then you should be able to solve most of the Wheastone bridge circuits problem. Alright?